definitely respond. So have you ever looked at water and wondered like what's in this? And if you have, then that kind of means it's fallen under biogeochemistry, because that's kind of what we're doing with biogeochemistry, is kind of looking at water systems, at least for me, and going, what's in this? So what is biogeochemistry? So biogeochemistry involves biology, which is the study of life in living organisms. So we're kind of looking at structure, function, growth, distribution, or evolution, or even other features of living organisms. It also involves geoscience, which is the study of the earth. And so that can involve processes that form and shape the earth's surface, looking at natural resources, and also how water and ecosystems are interconnected. And it also involves chemistry, which is the study of the composition, structure, and properties of matter. And it could be analytical, like doing chemical analysis or looking at wavelengths. It could be biochemistry, where we're trying to understand like biological systems. It could be inorganic, like looking at compounds and minerals. It could be organic, so focusing on carbon, or even PChem, which is physical chemistry, which is understanding chemistry and how atoms move. And those three are the fundamental sciences that make up biogeochemistry, which is the physical, biological, geological, and chemical processes and reactions that govern composition of and changes to the natural environment. And so that can include things like metal cycling and how metals move in the environment, and also like microbial reactions. So if you've heard about like bacteria, kind of how those relate to the environment and things like that. And so this is a picture of the Kamichi River, which is the river that I study for my thesis. And so when we look at it, it really doesn't look like anything's going on. We just see water, we see the sediment, we see trees and plants and the sky. But what we don't see happening is biogeochemical cycling. And so that's basically what are the reactions that are occurring between like the sediment and the water, the plants and the sediment, plants and water, and in the atmosphere. So kind of how everything is moving within this environment and sort of changing locations is what we call biogeochemical cycling. And we can look at metal cycling with biogeochemical cycling. We could look at nitrogen, phosphorus, sulfur, carbon, other nutrients, kind of a little bit of everything. It's just sort of how are things moving in the environment. And so with the Kamichi River, with metals, it's in southeast Oklahoma, flowing through Choctaw, LaFleur, and Pushmataha County. And here's a picture of it again. And it's one of the most ecologically diverse rivers in Oklahoma. It has around 80% of the total mussel species in Oklahoma. It has 98 fish species, 256 bird species, 55 mammal species, and 1,067 plant species. It's culturally significant, so it has 94 prehistoric sites that have been uncovered. And it also lacks salinity, so it's considered to be one of the most freshwater sources in the state of Oklahoma. So it's a very cool river. And since 2008, the EPA has listed lead, copper, silver, and zinc as impairments to the Kamichi River. And by impairments, I mean things that could be harmful to aquatic life or to human health. And that would be either for recreation or for drinking water, or just in hindering aquatic life from being able to thrive in the river. And I bolded zinc because zinc currently is the one metal that is still listed as an impairment in the river. And so we kind of can look at the land cover or land use of the Kamichi River Basin. And as we can see from this image, it's primarily covered in forest with minor exposures of grassland and cropland. And so that's really important because forests are really good at trapping metals within your system and keeping them there. And as we can see too, it kind of starts out with this like really clear blue color. It's very pretty. And then as we move down past different impoundments or lakes in the basin, we start seeing the water color sort of change to where it ends up being more of a murky brown color. And so this means that with the forests, which can help trap the metals, and with the impoundments, we can sort of start thinking about that maybe we're getting an increase in metals kind of over in the more heavily forested areas and down here due to both situations. And something else to think about with tracking metals is the geology. So if we look at the geology, it's primarily composed of shale and sandstone. And so shale contains a lot of metals in it naturally, and shale weathers very easily. So weathering shale could be a source of metals to a water system and to the Kamichi River. And if we look at the ecoregions of the Kamichi River, it's primarily the Ouachita Mountains and South Central Plains. And so these are really important things to consider when we're trying to figure out metal tracking and kind of like where they're coming from. And so metals in freshwater, metals are primarily introduced into the environment from weathering processes. So like was mentioned before, if like shale weathers out, that could introduce metals into a water system. From volcanic eruptions, so you guys will see volcanoes erupt and the ash come out. All that particulate matter also has metals in it that can then like deposit in nearby water systems, and also from human activities. So like if we have industrial plants or we build highways or railroads, all those would contribute metals into the system. So like if it rains on a roadway, the water on the road doesn't just stay there, it has to run off somewhere. And so that runoff is going to contain metals that could then make it into the system. Yes.
Yeah, so is there a baseline of metals usually in water, or is it something that humans have kind of just made really bad?
There is there's a baseline for naturally occurring, and then it's kind of based on a math equation, and then human activity has kind of made the situation worse, and we can sort of look at the math equation and figure out how much human activity has impacted the metal content in our water systems. And so examples of metals in water include arsenic, cadmium, chromium, copper, nickel, lead, and mercury, and there's also like lots more. And so metals in freshwater systems can pose environmental damage, and by environmental damage, I mean they can pose threats to aquatic life, because aquatic life is also subject to metal toxicity. They can pose risks to human health. So we drink water. And so if there's an increase of metals in our water supply, then that's going to pose health problems to us. Also the environmental damage as far as like recreation. If there's a water system that has really high metal content, you probably don't want to go do recreational activities in there, because we can still be absorbing metals in through our skin. And benthic organisms are the most affected. And so benthic organisms are organisms that live on the bottom of a river. And so those could be mussels. So they would be the most affected due to metals in the water. So how do we even track metals in the river? Like what do we do? How do we do this? So one thing we can do is do field work. So at least in the fieldwork that I do, we go out and we collect water, sediment, mussels, and lichens. And to sort of talk about lichens briefly, they're like little mossy structures that grow on rocks, and they trap atmospheric deposition. So anything that's in the atmosphere, lichens can take that in and accumulate it as they grow. So they're really good indicators about what's coming in to your surrounding water system from the atmosphere. And so we do summer and winter field work. So I guess, does anyone know why we would go in the summer and the winter and not just pick one time during the year to go?
Is it because of runoff?
Close. That's a good answer though. So kind of from water temperature influences aquatic life and water chemistry. So we choose to go in the summer and winter due to the different water temperature changes. And also there will be different amounts of runoff in both seasons, just because of about the amount of rain we get during summer and winter is different. So why wouldn't we move? Oh, okay. So in warm temperatures, we can dissolve more minerals. So minerals are what composes rocks. So we can dissolve more of that, which means we're putting more elements, metals, whatever's in those minerals into the water system. We increase electrical conductivity, which decreases the pH. So electrical conductivity is a measurement of the total amount of ions in water. And so pH is the measurement of hydrogen ions in water. And so if we're increasing in electrical conductivity and increasing the total amount of ions in our water, that means we're also going to be increasing the total amount of hydrogen ions in our water. And so pH is kind of like an opposite base scale. So if we're decreasing in pH, we're increasing in hydrogen ions and we're getting more acidic. So our water system, we would expect to see to get more acidic. And we also have less dissolved oxygen. So dissolved oxygen is just about the oxygen content within the water. So we would expect to have less oxygen in the water in warm temperatures. And then in cold temperatures, we're increasing in dissolved oxygen. So there's going to be more oxygen available to aquatic life. We're going to increase in CO2. And that's because if we're going to compare water to, or I guess we're going to compare river to soda really quickly. So cold soda cans are a lot more fizzy and have a lot more bubbles in them than a warm soda can. So, and that can be applied to rivers. So cold water in rivers is going to be able to have a lot more like gas trapped in it. So we actually would have an increase in CO2 gas in our water systems during winter conditions. And we're also going to decrease in electrical conductivity. So those total amount of ions are going to decrease in wintertime, which means we're going to increase in our pH. So we're going to get more alkaline or more basic. So we're going to start shifting and going this way and getting out of the acidic range. And water temperature also with aquatic life. So we all have our ideal temperature that we like to be at. So does aquatic life. So mussels prefer 65 degrees Fahrenheit. That's their ideal water temperature. And fish have an ideal water temperature. Aquatic insects have ideal water temperature. And so if our river isn't at that ideal temperature for different species, then those species are most likely going to choose not to live there. And if they're already there and the water temperature changes drastically, then that's going to cause them to start dying off. So water temperature is a big influence as far as biogeochemistry goes. And then we collect well water and surface water. So I was wondering if you guys had any guesses as to why. And I guess well water is groundwater, so it's the water beneath the surface.
Would well water have more minerals?
Yeah. So that's one thing is well water is going to have more minerals in it because it's in constant contact with the surrounding rock type. It's also going to have a different water chemistry to surface water. So this diagram over here shows we have A, which is a gaining stream. And so here's our river, and then here's our groundwater here. And these arrows show the direction of water movement in the ground. So the groundwater is actually moving into the river and increasing the water in the river. So that's what we call a gaining stream. And then we have the losing stream here. And so the arrows are indicating the direction of water movement. So the waters are moving down into the groundwater. So we're losing surface water, but it's going into the groundwater. And then we have it where it gets completely disconnected. So we're not getting groundwater going into the river, but we're getting the river water seeping down into the groundwater. And so we would call these surface water groundwater interactions. And so because of this, this can influence the water chemistry and generally too will influence the metal content in water systems because groundwater is going to have different metal content than surface water. Yes.
Is that configuration between the water and the surface or like the groundwater and the actual river system, is that going to create, is there an optimal, I guess, balance of it? Or is it always bad to be losing water to the ground or?
It would be bad to be consistently losing water to the groundwater. Ideally, ideally the best situation would be to sort of have like a gaining stream, but most rivers kind of go through both gaining and losing streams. So they kind of primarily go through A and B situations, and will be a losing stream kind of more so in summer conditions when it's warmer, and then there'll be a gaining stream more so in winter when it's colder, and do that. Yeah. So yeah. And so because of these like interactions, it's going to change where metals are at. So if we're in a gaining stream situation, the groundwater has more metals, and that's obviously going to increase metal content in our freshwater system. And just like if we have a losing stream, the metals are going to sort of seep down in the groundwater. So we collect well water and surface water so that we can look at these interactions and figure out, well, maybe metals are coming from the groundwater versus more so being in the surface water and things like that. And so we go back to the lab and we do lab work. And I do my analyses using an ICP-MS, which is an inductively coupled plasma mass spectrometer, and it is a mouthful. But basically what it does is just detecting, we can tell it what atomic mass to look at for specific elements, and it will look for those elements that we specify. And the really cool thing about this is we could actually look at every single element on the periodic table, but I focus on metals, so we only look at metals. And it will tell us the metal content that we have in the water. So like how much of it do we have? And I have this short video here to kind of go through what lab work kind of is like as far as prepping samples and doing all that. So we kind of digest our samples, and by digest, I mean we use concentrated acid, and we put them in these digestion tubes, which are made of Teflon and are safe to be put in a microwave. And the microwave that we use isn't one that we microwave food in. This one can go up to like 200 degrees Celsius. And so we microwave our samples at around 175 degrees Celsius. We wait for them to cool down because they're really hot when they come out. And we can pour them all out. And we basically have just liquefied our solid samples. We cannot run concentrated acid through an ICP-MS, so we have to dilute it. So that's sort of like the dilution process. And then we can kind of run the liquid sample through the ICP-MS and then analyze the sample. And after it runs through all of its replicates, we get data back for that specific sample that will tell us how much of each specific metal we have in our sample. And then we can solve like math equations that'll kind of tell us whether the metal content is more like anthropogenic, so kind of not naturally occurring, whether it's coming in from like human activity, or whether it's more naturally occurring and is primarily being sourced from the natural environment around us. So that's all fine and dandy for looking at like present day stuff and what's going on now. But how would we even track metal accumulation over time in a river, and like how do we track it historically? So that's kind of where mussels come in. So mussels are benthic dwelling, so they live on the river bottom. They provide ecosystem services, so they're actually a very supportive organism to have. They're filter feeders, so adult mussels can filter 15 gallons of water per day. And as they're filter feeding, they will take in everything. So they will take in metals in the water, anything else in the water, and then they'll release out stuff. But the metals, they don't release back out. They actually start accumulating them in their tissue and shell. So they will accumulate the metals as they grow over time. And they store CO2, so their shells are composed of calcium carbonate, which is kind of similar to limestone. And so their shells can store in carbon dioxide. And for the Kamichi River, there's been a 60% decrease in mussel population due to altered flow rate and due to a decrease in water quality. And so mussels are very vital to the ecosystem. And since they can take in the metals and sort of improve your water quality, if we start seeing a decrease in mussels, then that means something's wrong with our water system and it's not as healthy as it should be. So this is kind of like a little graphic about mussels. So again, like mussels are filter feeders, so they'll filter out pollutants and release nutrients. So they're actually nicknamed livers for rivers. So like our livers filter our blood, mussels filter the river, so livers for rivers. And water systems with mussels are a lot healthier than those without mussels. And then, like I had said before, mussels prefer 65 degrees Fahrenheit water. That's their ideal temperature. And they're very sensitive to changes in their environment. So if we see an increase or decrease in water temperature, then that's going to negatively affect the mussels. And pollutants and impoundments cause mussels to get sick. And if you have a mussel die off, your water system is not as healthy as it could be. And then mussels help combat climate change. So since their shells are composed of calcium carbonate, they can take in CO2 to help build their shells. So they can store CO2 from the atmosphere, even in the water, in their shells as they grow. And so their tissue, which is here, we can remove their tissue out of their shell once they're dead. And it kind of has a muscular foot that they had used for movement. It has their mantle, which had surrounded the shell interior and helped build the shell. Their head anterior and posterior adductors, which are used to sort of open and close the shell, so they can kind of like move like open like that. And labial palps and gills that they use for filtering, so they can take in the water and sort of filter what they don't want out. And so that kind of gives us like total metal accumulation if we study the tissue, and that's kind of everything. That's all the metals they've accumulated in their entire lifespan. Whereas with their shell, they have two. They have a left valve and a right valve, and they have three different layers. They have the periostracum layer, which is composed of organic material, a prismatic layer composed of calcium carbonate, and an inner layer composed of calcium carbonate as well. But within these shells, they have, it might be kind of harder to see in this image, but they have what we call like growth layers in there. And so each of those growth layers is going to correspond to a specific year that we can study. So, fun fact, did you know mussel shells are similar to tree rings? So tree rings contain information about each like specific year, and you can count the rings and get like ages back, and then you can study those rings and figure out what was going on at a specific year. Well, we can do the same thing with mussel shells. So they have growth layers, like was kind of pointed out before. So this is kind of a more so like up close in a microscope picture of a really thin section of a mussel shell. And so each layer is going to correlate back to a specific year, and we can do what we call laser ablation. So we just shoot a laser at the shell, and these dust aerosols are sent into the detector of the ICP-MS, and we can get ratios out. So we don't get content, but we can get ratios compared to calcium and see how much a specific element increased in relation to calcium. And so in this specific case, we can look at metals and see how much the metal content would increase or decrease in relation to calcium. And because each growth layer corresponds to a specific year, we can then get the metal kind of increase, decrease for specific years. And so it might be hard to see in this image, but there's like little dots in the growth layers. And so I'm going to show briefly like laser ablation. This is kind of what it looks like. So this is the laser that's lasering the shell. And what we don't see is like the dust aerosols getting generated because we're breaking through that surface of the shell. And then that would then go off into the detector and would read off the metals in there and also read off the calcium, so we could then ratio it out. And so that allows us to track metals over time, because we can go back in time and see like how are they fluctuating between the years. That can allow us to track metals in flood and drought periods. So with the fact that we can get ages with each growth layer, we can go back in the literature and see, you know, was this a flood period? Was this a drought period? And sort of see, well, maybe, oh, we saw an increase in metals. Was this flooding or drought? And then depending on which one it was, then that can also help us out with future analyses and start thinking about the future. And even if there's not in the literature with flood or drought periods, we can look at isotopes within the shell that will tell us whether there was a flood or a drought period going on. So we can figure that out as well if it's not in the literature. And we can also get seasonal like metal tracking data. So even within the growth layers, there's seasonal variations. So we could even like make the spot size really small. So this is 100 microns, which is still like very small, but we can go even smaller and get seasonal variations. So we can look and go, oh, 20 years ago in winter, this is what the metal content was like in the river, and get information like that. And also ages, so we can date each growth layer and figure out what year it corresponded to and figure out whether there is an increase or decrease in metals. Yes.
So we have one question that says, zebra mussels have gotten a bad rap as an invasive species, specifically in the Great Lakes, I believe. Can you explain or relate this to your discussion? Thanks.
Yeah, so zebra mussels do have a bad rap as being invasive species, and they've invaded a lot of North America. So with zebra mussels, the bad thing that they're doing is they're causing native mussel species to die off. So since both mussels are competing for like the same area to live in, and zebra mussels are much more tolerant than what we're finding out to with native mussel species. So zebra mussels are able to withstand more temperature fluctuations and more like water chemistry fluctuations. So they're more tolerant to these changes than what we're finding out with native mussel species. So they're ending up outlasting the native mussel species. And since they're competing for the same resources, it's causing the native mussel species to die off. So that's kind of why they're getting a bad rap. We can still do like the same analyses with them as far as like laser ablation and even looking at their tissue. And I think one thing we could do is sort of figure out like maybe when they might have started to invade, if we can go back and date like each growth layer and figure out, well, this is when they first started growing, so maybe this is when they invaded, or near when that happened, and do things like that. And then why is this important? So the US has around 3.5 million miles of streams, or like freshwater systems. And so we're primarily composed of streams and intermittent streams. And intermittent streams are streams that don't necessarily have flow during dry periods. So they will be lacking water during like drought periods. We also have like canals and artificial pathways and aqueducts, which are all like made from like human construction. And kind of to put the mileage in perspective, the entire width of the US, or I guess like with this part of the US here, is 3,000 miles. And so we could get 1,250 widths of the US by just lining up all the mileage of streams we have like horizontally. So we could get a lot of US widths by doing that. So we have a lot of freshwater systems, which is really cool. And yeah. And then with that though is the EPA tracks water impairments for every freshwater system in every state, each every 2 years. So like each state has to give a water quality report every 2 years and submit it to the EPA. And so with that, we come out with 305B and 303D impairments. So 305B are water systems that we have water quality data on, and we sort of know like what's in the water and what's sort of been impairing it. And then 303D waters are waters that pose threats to aquatic life or to humans as far as like recreation or drinking water. And so basically, if you look at the US, we have a lot of red for the 303D that would pose threats to aquatic life and or to humans. And the main categories of impairments that the EPA lists are bacteria, metals, and physiochemical parameters. So with the fact that we've been talking about metals and sort of like how we track them and how we get like present day and even over time metal tracking, we can use that to sort of figure out where these impairments are coming from, how they're related to the environment. So like how are they moving within their own water system, and even offer tips as far as remediation goes. So if we find like maybe during a specific season, we find the metal content suddenly increases, but it decreases in a different season, then maybe there's something related to that specific season that we can do to sort of remediate that and make the water healthier for aquatic life and for people around us. So that's kind of why it's important that we do these studies, is to sort of try and get our water systems healthier than they are now. And so to kind of like summarize the biogeochemical cycling, because I liked this image, basically we get to look at how everything's moving in the biosphere. So how everything's moving through water, sediment, plants, and in the atmosphere, and figure all that out. And it's like a never ending puzzle, which is why I like it so much, because it's really never going to be one simple answer. It's always going to be multiple puzzle pieces you're going to have to figure out and put together, which makes it really cool. Yes.
Were you interested in biology, geology, or chemistry first?
I was interested in biology and geology first. I got into it with gardening, and that was kind of my interest, was like plants and soil. And then I switched to just being interested in like geology and chemistry. So I kind of like left biology in the background and was like, I don't care about this anymore. And now I like all three. So I went through a fluctuation over undergrad, I guess. But yeah. And I guess with biogeochemistry too, just to kind of like throw it out there, it doesn't just have to be related to like water systems. So you could do if you're interested in like space science and studying other planets, and you don't want to study Earth, you could go study biogeochemistry of another planet and do that as well. So it's not just like related to studying the Earth. There's so many different avenues that you can go out and study, like other planets and what's going on over there, and do that too. And so I just want to say that you can be a scientist too. So I started a citizen science project in like early September, and I called it What's in Your Water. And I really should have called it like You Don't Want to Know What's in Your Water, because after getting data back, I was like, I don't want to know this. So, so yeah.
We do have a good question that's relating to this. So within the state of Oklahoma, what have you found to be the #1 contaminant in the rivers?
Oh, that's a good question. So I guess I'm gonna answer in terms of everything that I've been studying. So we've found chromium-6 in every single water system that's been studied through doing the citizen science project, and we've studied different systems in different locations of Oklahoma, and consistently chromium-6 has been above EPA standards and has been elevated. And I did research on it because I was really curious as to why, and found out that Oklahoma is one of the states for having the highest chromium-6 in their like drinking water supply. So that was a not so fun find to find out. But yeah, chromium-6 has been consistently high in our water.
And does that come from the same sort of thing, like the erosion and weathering and any human activity?
Yeah, chromium-6 will primarily come from human activity. It's like minorly naturally occurring. So it's primarily going to be introduced from either like, I guess like industrial plants, or from like even like types of paints and just other like human built things as kind of the main introducer of chromium-6. Yeah. And even from piping. So like there's certain types of water pipes you have that are really good. They're supposed to like keep your water like clean as they're treated, which they do. But if you have chromium in that water, then the coating of the piping is really good at converting the chromium you have in your water into chromium-6 and doing that. So then you end up with it in your water supply. So yeah. And yeah.
One more. Have scientists been able to mimic, I guess, the function of mussels in a river system artificially? So have they been able to design a filter that's as effective as mussels?
Ooh, that's a good question. Not that I know of. I will say that in Poland, and I believe in Michigan as well, they've implemented mussels to I guess, help protect citizens with water quality. So they'll put sensors on mussels, and they rotate mussels every 3 months so they don't like overwork them. But they'll put sensors on the mussels, and when the water quality gets too bad, which is when the mussels are just gonna like close up, then it'll shut off the water that's coming through there, and they'll know that, oh, the water has decreased in quality, so it's gotten worse, so we need to like treat it and figure out what's causing it to be worse. So they've started doing that and have implemented that, and that would be something really cool to see implemented in other areas of the US and even in other countries. But as far as synthetic mussels go, I don't think we've been able to do that. Yeah.
And I don't know if you addressed this earlier, but in the early days of the ecology movement, we heard a lot about acid rain. Is that a useful scientific term, or is that too broad to have any meaning?
No, we still use acid rain and still talk about acid rain. Yeah, and acid rain can be a contributor to at least the metal relationship in water too. So yeah, we still talk about it and still use it and still try and study it. Yeah.
Do you know the impact of chromium-6 on humans?
Chromium-6 is a human carcinogen, so it will cause cancer in humans. However, how it affects each individual person is gonna like depend on how much you're consuming of it, and also like your immune system response, so how your immune system is working. So it won't necessarily affect everybody the same way right away. Yeah.
Steve says, a group of us are on a quest to paddle a section of each river in the state of Oklahoma. Would there be a benefit to having us collect water samples from each section? And if yes, how would this best be conducted?
Yeah, if you want to collect water from like from each river you are paddling in, you can just collect it in a container. Like if you have any like glass or like plastic container that hasn't been used yet, and if it has been used, if you can like clean it out really well. And then I'm pretty sure you all aren't gonna have like acid on you. So if you can like keep it cold while you're doing that, by keeping it cold, it should help keep like metals and other things in the water and at least stop them from kind of falling out of solution. And then we could test it later on.
And then do you have any mussels you cannot analyze because they're endangered?
Yeah, so with doing this, it is against the law to study endangered species, or at least we can't go out and collect endangered species of mussels. And if we do, then we would get in a lot of trouble. So we only study ones that are not endangered.
All right, and we'll let you jump back into talking about the citizen science project.
Yeah. So kind of yeah, so it's what's in your water, and right now it's just focusing with Oklahoma water systems because that's where I live. If any of you are in other states and you're interested in water quality or like and sort of figuring out what's in your water, and this could be in like your local river, your local creek, your lake, ponds, even like your drinking water if you wanted to know it was in your tap water. Basically everything we do can be done for like any type of water. So whatever it is you're interested in, that's kind of the whole point of this project, is to like let you explore what water system you're interested in. And kind of right now we focus a lot on the Arkansas River, which is pictured here and here, and then have done a little bit with the Kamichi River, and we've also done some creeks as well. So like we've done Crow Creek, Bird Creek, and like Coal Creek in Oklahoma as well, and a little bit on the Illinois River. And basically we kind of like go out, get water, and test it on site. I've also had people like send water in and tested it, and we have a map. I didn't show the map here, but under like this tab map, you could go and look at basically all the data that we've gathered on every single site, and we've tested over like 50 sites already. So there's a lot of like data out there, which is pretty cool. And you can sort of see, and we've done like from the head of the waters, like all the way down to sort of the end of it, and which has also included like infrastructure projects. So we've actually seen how doing infrastructure in river systems has changed the water chemistry or added metals or decreased that. So like with the Arkansas River, they're reconstructing Zinc Dam. And so we've actually seen an increase in metal content as they started doing the reconstruction downstream of the river. So we're actually getting to sort of like watch the water chemistry change in real time in a way, and seeing how that's happening. And basically kind of at the end of this project, which I don't know when the end is going to be, so it's a never-ending project right now, but we would submit the data to the EPA for their water quality report. So, and since we follow all the EPA methods, the kind of one of the goals is to have it be included in the EPA water quality report. And so that way there's like more sites on waters that have data on there, which should also help towards like remediation options and making water safer to recreate it and drink, and safer for aquatic life too. So yeah. And if you're interested too with there's EPA criteria on the site as well. So if you wanted to go see like what the EPA standards are for water, for metals and for like organic compounds, or even for like physical parameters like temperature and dissolved oxygen and like total dissolved solids, they list, I've like linked to all the EPA criteria as well, so you can go see and how that changes depending on what you're sort of looking at for. So yeah, so you can be a scientist too. And if you're not able to get like water chemistry data, or you're not interested in getting water chemistry, and you just kind of want to go out to a system, even if you just take a photograph of the water system, and if you do that consistently, you're documenting physical changes of the system that may not that we may not already have. So even just taking photographs out of your local water system can be really beneficial too. Yeah.
Do we know what happens to the mussels if the rivers become like too saturated with metals? Like, are they able to protect themselves by just closing, or are there negative effects to the mussels?
Yeah, so if it becomes too polluted with metals, it'll cause the mussels to start dying off, because there'll be a point at which they would have taken in too much of it, and that's gonna cause them to have metal toxicity, and then they'll start dying off. And we've actually like seen it in the Kamichi River, where we've gone out and found mussels, but we've only found juvenile ones and then found dead ones, and the only live ones are juvenile. So we were actually seeing that the mussels weren't even able to make it past being like 5-8 years old at certain sites of the river. So yeah, it'll start killing off mussels.
Mm-hmm. And Pat says, what an outstanding presentation. We do hope people will start testing and find out what's in your water. And is this a website that the public is able to get to?
Yeah, it's a Google site. I guess I can send you the link or link to it.
Yeah, I'll definitely post it on our page after this is completed.
Yeah. And if you have anything you want to submit, like there's a submit data option on the website too, and you can submit like pictures or data, and it's a Google form really, so it kind of lists out specific things, so you don't have to remember like units or what it was that you were submitting. And there's also like a contact link too, so if you wanted more information, you can submit that thing and it goes straight to me, and I'll respond.
Well, perfect. Lauren, thank you so much for joining us this morning. This was an excellent talk and definitely broke it down in a really good way, because biogeochemistry is a lot of science all in one.
It is, yeah. Thank you for having me. I had fun talking about biogeochemistry and tracking metals in water.
And if anyone has any follow-up questions, go ahead and ask them, and I will track Lauren down in the future. I hope everyone has a happy Thanksgiving holiday. Thank you.